Hello again. In this video we will discuss the Zener diodes. Zener diodes operate in the breakdown region and they operate also in the opposite direction of the normal diode. Let me explain what I mean. In the Zener diodes, the cathode is the positive compared to its anode. So when the current flows from the cathode to the anode, the Zener will operate, it will be on. Whereas in the normal diode, if the current flows from the anode to the cathode, then the diode is on. Okay. In the previous videos, I showed you the IV characteristic of a non-ideal diode, and this is the breakdown region. This is the threshold where it enters the breakdown region. A more detailed diagram is here. This is the IV, this is the very steep IV curve that the diode exhibits in the breakdown region, and the almost constant voltage drop that this indicates suggests that diodes operating in the breakdown region used in the design of voltage regulators. Now, what is a voltage regulator? A voltage regulator is a circuit that provides a constant DC output voltage in the face of changes in their load current and in the system power supply voltage. Such diodes are called breakdown diodes or Zener diodes. Okay. Now, when a Zener diode is operating, it can be replaced with a DC voltage source called VZ node and a incremental resistance RZ. Okay. So one of the equations is just an Ohm's law where VZ is equal to VZ node plus IZ RZ. And the other equation is similar to the small signal where delta VZ is equal to delta IZ RZ. Let's take an example. The question says, the 6.8 volt Zener diode in the circuit of figure 4.19a, this is the figure, is specified to have a VZ of 6.8 at IZ 5 milliampere. Now, I told you before that whenever you see an at, this means it's a sample, right? RZ is 20 ohm and IZK is 0.2 milliampere. Whenever you see IZK, it represents the minimum current for the Zener to operate in the breakdown region. Let me write this down. The minimum current required for the Zener to operate in the breakdown region. Okay. Now, the supply voltage V plus is nominally 10 volt but can vary by plus minus 1 volt. Now you can consider nominally as normal DC. Normal DC. Okay. So the DC is 10 and the AC is plus minus 1 volt. Why is this AC? Because there's a plus minus, there's a change, and this is constant DC. Okay. Part A of the question says, find V naught with no load and V plus at its nominal value. So we should have only DC. Let's redraw the circuit. Here we have a V plus equal to 10 volt. Okay. This is our resistance. This is the Zener diode, and there's no load resistance. Okay. Now current will be flowing in this direction from the high potential to the low potential, hence the VZ will be on. Okay. And if it's on, we will replace it with a voltage source VZ naught and a resistance RZ. Okay. Now, we need to find V naught. In order to find V naught, we need This is the equation of V naught. V naught is equal to what? V naught is equivalent to Vz. V naught is equivalent to Vz. Okay? But we cannot say that it's 6.8 because this is a sample. From the sample, we have to compute the Vz naught. After we compute Vz naught, we can find the Vz, which is equal to V naught. Okay, so in order to find V naught, we need Vz naught, we need I Rz. Okay, now again, we cannot say that Iz is equal to this Iz because it's a sample. Okay, we will use this only for computing Vz naught. So let's first compute Vz naught. Vz naught is equal to Vz minus Iz Rz. Vz according to the sample is 6.8 and Iz is 5 milli. 6.8 and Iz is 5.8 milli. And Rz is 20. This will give us 6.7 volt. Okay, now after computing Iz naught, let's compute I. What's I? I is the total voltage divided by the total resistance. I is the total voltage divided by total resistance. What is total voltage? It's 10 minus Vz naught minus the ground. This ground. Divided by total resistance, which is 0.5k plus Rz. Let's substitute in numbers. 10 minus 6.7 minus 0 divided by 0.5k plus 20, which is equal to 6.35 milliampere. Now after computing I, now we can find V naught. Now V naught is equal to 6.7 plus 6.35 milli multiplied by 20, which is equal to 6.83 volt. Okay, this is part A. Let's go to part B. Find the change in V naught resulting from a plus minus 1 volt change in V plus. Note that delta V naught divided by delta V plus usually expressed in millivolt over volt, and it's known as line regulation. Now we need to find the change in V naught, which is we need to find the delta V naught, which is AC, right? Because there's a delta, so it's AC. Now we need to convert the circuit to AC. In AC we have to kill DC. So V plus will be plus minus 1 volt. This is the resistance 0.5k, and this is Rz. Okay, this is V naught. Now how can we find V naught, delta V naught? What's the relationship between this delta V naught and this V naught? It's actually the same. Why? Because the input is AC. If the input is AC, which is changing, therefore the output will be also AC. It will be changing. Hence, delta V naught is equal to V naught, which is equal to what? We can actually do voltage division. If you change the design of this circuit to the following, then you will see it as this. So how can you find V naught in this design? It's actually what? It's actually voltage division. So it's plus minus 1 multiplied by Rz divided by Rz plus 0.5k. Okay, this will give us 38.5 millivolt. Okay, now this is delta V naught. If you want to find the line regulation, we need to divide the delta V naught by delta V plus. So line regulation is equal to delta V naught divided by delta V plus. Delta V naught we just computed as 38.5 millivolt, and delta V plus is this, right? Because it's AC, so it's delta, it's the same thing, divided by plus minus 1 volt. So the answer will be 38.5 millivolt over volt. Okay, this is the answer. Let's move on to the second part. This is part B, this is part A. For part C, it says find the change in V naught. Again, there's a change in V naught, hence AC, resulting from connecting a load resistance. Now we have a load resistance RL that draws a current IL equal to 1 milliampere, and hence find the load regulation, which is delta V naught over delta IL in millivolt over milliampere. So part C, we need to find delta V naught and the load regulation, which is delta V naught over delta IN. Let's redraw the circuit, because now we have a load resistance and we are in the AC due to the change 0.5 kilo ohm RZ. Now note that here we killed VZ naught because VZ naught is DC. Let's continue. Here is our load resistance RL ground. Okay, so now we have IZ and IL. Okay, because now here we have a change in current, we can use this equation. Delta V naught is equal to delta IZ RZ total. Okay, I think I forgot to put total here. Okay, now what is delta IZ? IZ, we have discussed this in the small signal, if you remember. Delta IZ is IZ new minus IZ old. If you compute this and simplify, you will end up with minus IL. So delta IZ is always equal to what? Minus IL. So here, delta IZ is minus IL, and IL was given in the question to be 1 milliampere. So IL is 1 milliampere, 1 milli, and RZ total is only 20 because we have only one Zener resistance. Okay, so the answer will be minus 20 millivolt. Now what is delta IL? Delta IL is IL new minus IL old. IL now is 1 milliampere, while IL old in the previous part there was no IL, there's no load current. There was no load current. So IL old is 0. So here it's 1 milliampere. Now the load regulation, which is equal to delta V naught over delta IL, it's equal to minus 20 millivolt over 1 milliampere, which is equal to minus 20 millivolt over milliampere. Okay, we're done for the third part. Let's move on to part D. Part D says find the change in V node when RL is 2 kilo ohm. Now RL is 2 kilo ohm. We need to compute again VZ delta V naught. So we need to find the change in. Let's try to copy this. We need to find the change in V naught when RL is okay. We need to find the change in V naught when RL is 2 kilo ohm. Let's redraw the circuit. V plus is plus minus 1 again because we are in AC due to the change. Here it's 0.5 kilo ohm. We have RZ grounded, and here we have the RL. which is equal to 2 kilo ohm. Now again, there's a difference in the currents, so we have to use this equation. Delta V naught is equal to delta IZ RZ total. Delta IZ is what? It's minus IL. What is IL? IL can be approximated as V naught over RL. So it's minus V naught over RL, and V naught was 6.8. Okay, it's just an approximation, so we'll take it as 6.8 divided by 2K, which will result in minus 3.4 milliampere. Okay, going back to the main equation, minus 3.4 milli multiplied by 20, which will give us minus 68 millivolt. Okay, this is part D. Part E says find the value of V naught when RL is 0.5 kilo ohm. So they have changed the load resistance. We need to find V naught. Okay, let's redraw the circuit. V plus, here we have 0.5K, RZ, and this is RL. Okay, RL is 0.5 kilo ohm. Now what was I? I was, from the first part, 6.35 milliampere. 6.35 milliampere. What's IL? Let's compute IL. IL is V naught divided by RL. V naught was 6.8 divided by 0.5K will result in 13.6 milliampere. Okay, now you have to think a little bit about this number. Now this number is 13.6 milli. The total source is 6.35. So how come that the source is 6 and what's leaving is 13.6? What does this mean? This means that IZ has to be in the opposite direction, right? Because 6 plus something has to add up to 13.6. Now, if IZ is in the opposite direction and the Zener was, the shape of the Zener was like this, will the Zener be on or off? It's actually off, right? So the Zener is not operating in this case because IL is much greater than I, which is the total source. So here Zener is off. Okay, so now we have to replace the Zener with an open circuit. V plus 0.5K. This is an open circuit, ground, and this is the 0.5 kilo ohm load. This is V naught. Now if you want to find V naught here, what can you do? Okay, if you want, you can simplify this further because the current is in series and it will look like this. Okay, so if you want to find V naught here, what can you do? You can do either nodal analysis or voltage division. Voltage division is much easier. So let's do it's V plus multiplied by 0.5K over 0.5K plus 0.5K. The numerator, this 0.5K is actually this one. Okay, what is V plus? V plus is 10 because we are now in the DC. It's 10. Yeah, the question says find the value of V naught. It's not a change, it's only V naught. So V plus is 10, and you will end up with 10 multiplied by half, which is 5 volt. Okay, this is part E of the question. Let's move on to the last part. What is the minimum Let's see. I can decrease the size. So it says, what is the minimum value of RL for which the diode is still operating in the breakdown region? Now we need to find the minimum value of Rn. Let's go back the previous two parts. When RL was 2K, nothing was wrong. The Zener was operating. But when the load resistance fell to 0.5K, the Zener became off. Now we need to find the minimum RL so that the Zener still operates in the breakdown region. So the number has to be between the 0.5K and between the 2K ohm. Let's see. V plus, this is our resistance, 0.5K, VZ naught, RZ, Rn. Okay? Now, we are looking for RL, so we have to do Ohm's law, which is V naught minus 0 over IL. Okay? What is V naught? Okay, we need to find the minimum V naught. Minimum V naught is approximated as VZ naught, which is equal to, in part A, it was 6.7 VZ naught. Okay? When finding the minimum, we need to find the minimum V naught, which is VZ naught, which is equal to 6.7 volt. Okay, so what we are left with is IL. How can we compute IL? Using KCL. Okay, so IL is equal to I minus IZ. I is equal to, it's different from part A because here V plus has to be minimum also. Now in part A, V plus was 10 and V naught was 6.8 or 6.83. Whereas in our example now, we are finding the minimum. So the minimum voltage is 9 volt. How come? I will explain. Now, if you remember, V plus was what? It's 10 plus minus 1. If you want to plot the waveform of this, okay. The DC is 10, so the offset is 10. Then we need to go 10 plus 1 and 10 minus 1. So here the maximum is 11 and the minimum is 9. So because we are finding the minimum resistance, we need to equate V plus to be 9 volt. Okay? What is I? So now I, we can do Ohm's law. We can say I is equal to 9 minus V naught over 0.5K, which is equal to 9 minus 6.7 divided by 0.5K, which will result in 4.6 milliampere. 4.6 milliampere. Okay? And IZ has to be minimum also. And we said earlier that the minimum I for operating in breakdown region is called the IZK. And IZK is given in the question as 0.2 milliampere. So IZK is 0.2 milli, and you will end up with 4.4 milliampere. Plugging the numbers again in the main equation. V naught is 6.7 over 4.4 milli will give us almost 1.5 kilo ohm. Now note that this number makes sense. Why? Because it's in between 0.5K and 2K, which gives us a hint that our number is correct. Okay, so we're done for the first question. Let's move on to another question. Let's see, what does this question says? It says, a Zener diode whose nominal voltage is 10 volt at 10 milliampere has an incremental resistance of 50. What voltage do you expect if the diode current is halved, doubled? What is the value of V0 in the Zener model? Let's compute only VZ0 when the IZ is changed. So when IZ is 10 milliampere, VZ0 is equal to VZ minus IZ RZ. VZ0 is 10 minus IZ, which is 10 milli, and RZ is 50. This will give us 9.5 volt. Okay, and when IZ is halved, hence 5 milliampere, VZ0 will equal to 10 minus 5 milli multiplied by 50, which is equal to 9.75 volt. And when IZ is doubled, which is 20 milliampere, VZ0 will equal to 10 minus 20 milli multiplied by 50, which is equal to 9 volt. So as you can note here that when IZ is doubled, the voltage decreases, and when the current is halved, the voltage increases. Okay, moving on to the next question. The question says, a Zener diode exhibits a constant voltage of 5.6 volt. This is Vz. For currents greater than 5 times the knee current. The knee current is IZK, which is 1 milliampere. So IZ is 5 times IZK. So it's 5 milliampere. Okay. The Zener is to be used in the design of a shunt regulator. Shunt regulator is the following: V plus, I'm not sure what is the resistance here, let's keep it R. This is Zener, and this is the load regulator. So this is the design of a shunt regulator. Okay, now the Zener is to be used in the design of a shunt regulator fed from a 15 volt supply. The load current varies over a range of, so IL ranges from 0 milli to 15 milliampere. Find the suitable value for this resistance R. If you want to find R, then we need to do Ohm's law, right? So R is equal to 15 minus V0 over I. V0 is Vz. V0 is Vz. Okay, so it will be 15 minus 5.6 divided by I. What is I? I is actually KCL. So we need to do KCL now. It's IZ plus IL. IZ is 5 milli, whereas IL is in the range from 0 to 15 milli. So we need to take the worst case scenario, which is 15 milliampere. So here we're having 20 milliampere. Why is 15 the worst case scenario? Now when IL is 0, the total I will be only 5, because 5 plus 0 is 5 milli. So then you will compute the resistance. Now this resistance that you computed, assuming I is only 5 milli, will not tolerate the new current if IL is 15 milli. Because when IL becomes 15 milli, the total current becomes 20 milli. So the resistance that you computed based on I is maximum 5 milli will not comprehend the 20 milliampere current. So we will take the worst case scenario, which is 20 milli, and this will result in R equal to 470 ohm. 470 ohm. Okay. Now, part B of the question says, what is the maximum power dissipated in the Zener diode? We need to find the maximum power across the Zener diode, P max, PZ max, which is IZ max multiplied by Vz max. Now Iz is varying, however Vz is fixed. It's what? It's 5.6. Now what is the maximum current? What is the maximum Iz? If you want Iz to be maximum, then you need to eliminate the load resistance. So IL is 0. When IL is 0, then I will equal to Iz. Hence, Iz is equal to I, which is 20 milli. This is the maximum power, which is equal to 112 milliwatt. Moving on to the next question, which is the last question before we end this video. Okay, so the question says a shunt regulator, hence we have to draw its design. We have a V plus resistance and a Zener diode. By the way, I did not tell you why the Zener diode has this wiggly line. It has this wiggly line based on the IV characteristic. See, this line is also wiggly. So based on this design, they have given this shape to the Zener. Okay, let's continue. Okay, so a shunt regulator utilizes a Zener diode whose voltage is 5.1 volt. So this is Vz at a current of 50 milliampere. So Vz is equal to 5.1 volt. Iz is 50 milliampere, and whose incremental resistance, which is Rz, 7 ohm. The diode is fed from a supply of 15 volt, so V plus is 15 volt, nominal voltage through a 200 ohm resistance. So R is 200. Okay. What is the output voltage at no load? Find line regulation and load regulation. Let's begin. So part A, we need to find V naught. We said V naught is equal to Vz naught plus IRZ. So in order to compute V naught, we need to find Vz naught. Vz naught is equal to Vz minus IZ RZ. Vz was 5.1, Iz is 50 milli, and Rz is 7. This will result in 4.75 volt. This is Vz naught. Now, I total, which is here, is total voltage over total resistance, which is 15 minus Vz naught minus 0 divided by R plus Rz. So this will result in 15 minus 4.75 minus 0 over R, which is 200 plus 7. This will give us 49.5 milliampere. After finding Vz naught and I total, we can compute V naught. Plus 49.5 milli multiplied by 7. This will give us 5.1 volt. Okay, now it's more accurate than 5.1. I think it's 5.109, something like this. Okay, so part B, we need to find the line regulation. Line regulation is in AC, so here we have to kill DC. The question did not give us any information about the AC voltage, so we'll keep it unknown. This is 200. This is Rz. Okay, and we do not have a load resistance. Okay, part A actually said that there's no load resistance, so the circuit will be like this: 15 volt, 200, and because the Zener is on, it will be Vz naught plus with Rz grounded, and this is V naught. There's no load resistance. Now for part B, we need to find the line regulation. Line regulation is equal to delta V naught over delta V plus over delta V plus. Delta V naught is equal to V naught in this case because the input is AC, so we will do voltage division. We will keep the AC source unknown, so it will be RZ divided by RZ plus 200. Okay, and delta V plus is equal to V plus, hence the line regulation is equal to V plus 7 over 7 plus 200 divided by V plus. V plus and V plus, they cancel each other out, and you're left with 7 over 7 plus 200, which is equal to 33.8 millivolt over volt. Okay, this is the line regulation. Now the load regulation, okay, for part C, which is the load regulation. Load regulation is equal to delta V naught divided by delta IL. Okay, in order to compute the load regulation, we need to have a load resistance. Let's assume that IL is 1 milliampere. Now let's redraw the circuit. This is V plus, this is 200 RZ and RL, where IL is equal to 1 milliampere. So delta V naught is equal to it's equal to delta IZ RZ total. We use this equation because now we have a load resistance and there is a change in the current. Delta IZ is equal to minus IL, which is equal to minus 1 milliampere. So here we have minus 1 milli multiplied by 7, so we will end up with minus 7 millivolts. Delta IL is IL new minus IL old. IL old, there is no old load resistance, so it's 0, and the new IL, which is the current load current, is 1 milli, so here it's 1 milliampere. Okay, so the load regulation is equal to delta V naught over delta IL, which is equal to minus 7 millivolt over 1 milliampere, and you will end up with minus 7 millivolt over milliampere. This is the load regulation. Okay, so now we have ended the Zener diode. In the next video we will discuss some graphing in the diodes, and then we will conclude chapter 3. Thank you for listening.